Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
He and a few other people had independently different takes on that, but it now, in retrospect, seems like an obvious thing, and Tom works to make it more obvious with every passing day. And then he moved off in a sequence, which I may review to some extent, to work at INEAC, Switzerland, on character recognition and other forms of document analysis. And then he was also, for time, at IBM's Alvord Research Center, and also at Xerox PARC, basically working at well-known and reputable document analysis group in the world, which is no longer Xerox, the so-called Xerox. But that group is now kind of under its own diaspora. So he will talk to us today about the most simple way of trying to formulate this problem, which I find strikingly simple yet powerful at the same time. Thanks very much.
Yeah, so this is stuff that just won't go away from my research agenda. It's just turned out to be so powerful and useful, and I'm going to talk about the latest version of it, which uses interval arithmetic and brings together geometric matching with global optimization techniques that have been known now for about 25 years. And, well, I'm going to tell you about the techniques and then show you a lot of applications, kind of cartoon-like. And I have to say, I actually haven't held this talk before, so this is completely fresh and new. The method itself actually has been written up in pattern recognition letters, which is actually a format that I like because it allows you to write conference-like papers without having to travel to a conference, which, depending on where the conference is, may be good or not. But anyway, so let's see how it goes. I'm going to be talking first about geometric. Actually, these techniques turn out to be applicable to a lot of different geometric problems. And I'm going to be first talking about geometric problems as optimization, in particular the example of point matching. Then I'm going to give you a brief overview of interval arithmetic, then global optimization using branch and bound methods and interval arithmetic, and then some ongoing work. And then I'll be giving you lots of other problems and applications that can be solved with this. And time permitting, at the end, I'm going to show you kind of how to put these together into a simple geometric layout analysis system. So what is geometric matching? Well, one formalization is the following. We have a set of points, model points in R2. Let's just talk about 2D matching. And a set of image points. And somewhere in these image points, these model points are to be found, but there may be some error on the location of these points. There is lots of clutter, meaning there are lots of points that don't belong to the model, and some of the model points may also be missing. And what we're looking for is a transformation that maps model points into the image that brings model and image points into close correspondence. And the set of transformations that we consider is something that we specify at the beginning. That's part of the problem specification. So let's think of this, for example, just for the purposes of this discussion, as translations and rotations, 2D translations and rotations. So there are 3 parameters we need to specify in order to transform the model and place it in image space. An X translation, a Y translation, and a rotation. And then there is one more thing that we need in order to specify the problem, and that's an error model. So after we've taken the model and transformed it into the image space, we then find nearby points and measure the error in location between the transformed model point and the corresponding image point. So, it always does that. So what we need in order to specify a geometric matching problem is a list of image points and a list of model points. Actually, and I reversed these. A set of allowable transformations T and the quality of match function Q of T. So let's look at these in a bit more detail. So in the traditional least square matching framework, what we say is we have our image points B. I mislabeled them on the previous slide, but we have our image points B, and we have our predicted image points, which I call BI pred. So we obtain those by applying the transformation to a model point. And then the error, the squared error that we compute is the minimum over all the over the distances between a predicted model point and all image points. So it's the least square distance of the transformed model point to basically its closest image point in the image. And then there's a square missing here too. Then the total quality of match, the least that we assign to a particular transformation, is just the sum of all these squared errors. And if we minimize that, we get a least square match of the model against the image. Now, this is actually not really all that useful in the presence of clutter, in the presence of spurious points in the image. This is actually not a good way of matching. So instead, what one does is one performs robust least square matching. So in that, you basically impose an upper limit on the error that each feature may contribute to the total quality of match function. And this can be justified in a simple probabilistic model, which we won't have time to go into here. But what we basically say is we say that the error for model point I, the predicted error, is just the minimum of some maximum error and the squared error that we computed before. So it turns out it's actually convenient to rewrite this. So this was the robust least square error formulation that we had on the previous slide, but it's actually nice to rewrite this by introducing this function phi, and instead of minimizing the error, we maximize this quality of match function, which basically looks like, do we have any pens here? Yeah. Which basically looks something like this. So for zero error, we add 1 to the score, to the total score for that transformation, and then at a distance of epsilon, we just don't count this as a match at all anymore. And this is this is nice because it actually also generalizes. We can also use other, bounded error matching in particular can be written in the same framework by basically choosing this as the phi function. So this says anything that matches to within an error bound of epsilon counts 1 towards the total score, and anything that's outside counts 0 towards the total score. So this is a problem that people have tried to solve for a long time, optimizing this quality of match function. I mean, there's the Huff transform, there's ransack, or closer related gradient descent with random restarts. gradient descent with alignment or search. The expectation maximization algorithm has been used for this, something called pose clustering, and just any imaginable heuristic global optimization method has been applied to this, so simulated annealing, genetic algorithms, whatever. And then there's been actually one algorithm that's quite nice is hierarchical chamfer matching by a Swedish woman whose name I'm not quite sure I can do justice, but anyway, all of these have some limitations, so none of them are globally optimal. So you don't actually know when you get a solution out of them whether they are, whether you missed the right solution to the problem because the algorithm failed or because your model was wrong. If you try to use something like a Hough transform, for example, for geometric matching, you end up spending a lot of time tuning various parameters. So this is not a minor problem. It's you end up spending a lot of time tuning bin sizes and search depth and so on for these kinds of traditional heuristic algorithms. Then in the 1990s, there were a bunch of developments. There were two polynomial time algorithms that Todd Cass and myself came up with. One is based on a tree search method with pruning. Another one is a sweep of a geometric arrangement. Both are polynomial time, but they're slow. And then in '92, I introduced globally optimal geometric matching using branch and bound algorithms. And this probably was the first algorithm that was practical, the first globally optimal algorithm that was practical for these kinds of problems. Then in '93, there was work on Hadenlocher and Ruckledge came up with Hausdorff matching, which uses similar ideas about bounding, but it only works for Hausdorff metrics and only for a special set of transformations. And then there's been somewhat more work over the last decade on computational complexity and on refinements to these basic ideas. So the approach I'm going to be talking about today takes these branch and bound geometric matching ideas and combines them with global optimization based on interval arithmetic. And I'm not sure, has anybody seen interval arithmetic before here? Or so let's look at this in more detail. And it turns out, looking back, one could have just if one had thought of geometric matching as a global optimization problem, and if this had proceeded logically, one would have in 1980 opened up a book and looked at global optimization methods and said, oh, there's one using interval arithmetic, why don't we try it? But that's not the way computer vision developed. And it turns out there are also some computational tricks that are important to actually make this work well for geometric problems. So, interval arithmetic, what is it? Well, it's basically a way of extending the meaning of functions and operators from points to intervals. And the basic definitions, I'm not going to give a formal definition. There are lots of technical details, lots of different kinds of interval operators you can define, etc. But the basic idea is that if we look at a function f over some interval, we define the interval value of this as kind of an interval extension of that function as the minimum that function, the minimum value that the function assumes when we take its argument out of that interval, and the maximum maximum value that function assumes if we take its argument out of that interval. And similarly, for an operator like plus, minus, times, or divide, when we combine two intervals instead of two real values with it, we again define, we can again try and look at that as the minimum value that the combination of any pair of values coming from these two intervals assumes, and the maximum value. So if we do this for the basic operators, for the basic arithmetic operators and functions, and then we take some arbitrary arithmetic expression, we can just formally replace the real variables, and the real valued functions and operators in there with interval versions. And what we get out of that is an interval function, something that takes a bunch of intervals as arguments and returns another interval. And this interval is guaranteed to be upper and lower bounds on the actual value that the function can assume over any combination of input values taken from its input intervals. However, these bounds are not necessarily tight, and in fact, they depend on the exact arithmetic or on the exact algebraic form that we used for writing the expression. So just because you have just because two things are equivalent in terms of real numbers doesn't mean they're equivalent. They give you the same intervals as interval arithmetic expressions. However, under some simple conditions, they're equivalent in the sense that they're all convergent, meaning that as you make the argument interval smaller, the output interval becomes smaller in a predictable way. And that's really all we need for optimization. And this is actually the way Hampson used interval arithmetic for global optimization in the late 70s and 80s. So let's try and get a bit more concrete here and relate this back to the optimization of our quality of match function. So what we want to find is the transformation that maximizes Q of t. And we are looking at a transformation that consists of a translation, so an x translation, a y translation, and a rotation. And if we look at the interval version of that, we get an interval vector or a box. So we get the product of a range of x translations, a range of y translations, and a range of rotations. And what happens now if we consider the interval version of this quality of match function, which I've indicated just by little brackets here. I'm not going to use them consistently. I just put them here to indicate that these are intervals. So if we take this and plug it into the interval version of the quality of match function, we get upper and lower bounds for the quality of match for this range of parameters. So we're guaranteed that that the quality of match for any transformation t that's contained inside this box is between this upper and lower bound. So the core idea then behind this kind of optimization is that we start with a box that represents all the parameters we're interested in searching. So if we're interested in matching a model across an image that's 1,000 pixels wide and 1,000 pixels tall, then the range of translations would be 0 to 1,000, 0 to 1,000, and the range of rotations would be 0 to 2 pi, because it might get arbitrary orientations. And what we can do now is we can compute these upper and lower bounds, and another operation we can do is we can subdivide this box, for example, into 8 equally sized sub-boxes along each dimension, and then for each of these sub-boxes compute bounds. And we'll see in a second how that fits in, how that gives you a global optimization algorithm. But let's just look a little more intuitively what this means. So here I just have a two-dimensional parameter space, and that represents the three-dimensional parameter space. But it basically says we have this box of parameters here in parameter space, and corresponding to that is a large number of possible different ways of placing the model into the image. So this parameter, the set of parameters at the top left corner of the box might correspond to this transformation of the model into image space. The one at the bottom right might correspond to this one, etc. And what we're using as the upper bound for our quality of match function is basically the quality of match we get assuming that all these points match, all the points that could possibly match under any of these parameters, they all match. That's our approximation, our bound. And what happens if we subdivide this box in parameter space is that we basically eliminate some of these possibilities. So if we just take sub box 1, then maybe we just get these two green, we only get possible transformations that correspond to, for example, these two green examples, but of course there are infinitely many, so you should think of this as sweeping out a set of possible matches, but we've also eliminated a lot of them. So with this, our bounds, we would expect our bounds to get tighter. So this kind of geometric view was actually the way these bounds were computed in earlier versions of this algorithm. But with interval arithmetic, you actually don't have to think about this. You don't have to actually go through the geometry and work it out, because you just write down the quality of match function, and in terms of real numbers, and then replace the real variables with interval arithmetic variables. So in something like C++ or C#, you can actually just go in and do that. You just change the declaration. So the overall branch and bound matching algorithm is now as follows. The main thing is we maintain a priority queue, and the items in this priority queue are an upper bound on the quality of match, which we compute using the interval arithmetic version of Q, the parameter region that we search, and a list of possibly matching candidates. And we start this, and I'll talk about this list in a bit more in a second. And we start off this list, initially we can set the upper bound to infinity. The parameter region is all of parameter space, and the set of candidates is all features, or all feature correspondences. And what we do in the main loop is we dequeue one of these things, and we get a new parameter region T and a candidate list. And if the box, if this range of parameters is numerically accurate enough, we accept it as a solution. There are actually more complicated acceptance criteria, but in practice this is actually good enough. And if it's not accurate enough, then we subdivide T into sub-boxes. We evaluate the quality of match function as before, and in the queue, we put back into the priority queue these subdivisions. So one thing that helps quite a bit with this is to maintain a list of candidates. And the idea here is that once the quality of match function, so the quality of match function is a sum of a bunch of phi's. And once this term has dropped to 0, it will stay at 0 no matter how much further we subdivide this. So that means that we actually only need to carry out this sum over the non-zero terms, and we can keep track of the non-zero terms, and that's actually what this list of candidates is. And whenever this drops to 0 for one of the terms, we just drop it off the match list and never consider it again in any of the children of that node in the search tree. So one one consequence of this is this actually kind of implicitly constructs a point location data structure. There have been some attempts at speeding up geometric matching by using point location data structures, and for many approaches it helps. So for example, if you do a recognition by alignment, using a point location data structure for finding matching points helps a great deal. But with this matchlist trick, the search tree itself becomes a kind of point location data structure. So there's, yeah?
Is a candidate a point, a model point, or is a candidate a key? I think it's a model point. Okay. And then you could be wrong.
Okay, sorry, I've been, yeah. So let's go back. So, yeah, that is probably confusing. So let's go back to the algorithm. So there are these items in a priority queue, and in this slide I just refer to them as items. But here by candidates I mean I actually mean the correspondence between individual models and features. So this error here is actually so for each possible So we have our model points and our image points, and for each transformation and each model point and each image point, there is some sort of correspondence between the two. And this gives rise to one of these error terms, error ij, and that's actually what I refer to candidates here. So, yeah.
That's a fair
image. Yeah. So, yeah, that's a good question. It actually becomes a little simpler. So I picked this example, the geometric matching, because that's what I advertised. It's actually a little simpler to think about this in terms of, for example, line matching, which is actually where it was originally developed. So in that case, the model drops away, and you just talk about the image points that could still match a line hypothesis. So the list of candidates there is just the set of image points. But we'll see that in the, yeah. So there's a lot of tricky detail kind of in the implementation here. I mentioned a few more things later. So I don't expect that after this talk you'll be able to just sit down and implement it. Although once you get the details and tricks, it's actually not a very difficult thing to implement. So anyway, this just gives you an example of how this search actually progresses. So this is just the model consists of these points, the image consists of these points, and this is the transformation space. It's actually R3. So these are the X translations, Y translations, and then rotations are out of the axis, and all the subdivisions are just projected down. So what you see is that there's kind of an okay match, possibly here, here, and here, but the algorithm really just zooms in on the solution, which is here. And here's actually a practical application of this, which is actually not with this version of the algorithm. This is with a very early version, which is bounded error view-based recognition and clutter. So the idea here is just to take a moderate number of 2D training views and then perform 2D matching in order to find instances of this 3D object in actual scenes. This was actually the motivation for developing this algorithm, namely to establish that 2D matching is in practice a good way of performing 3D object recognition. But that's a separate and long argument. Yeah.
Again, about the updating of the list of matching points. So you subdivide the parameter space, not the list. So how do you update these list of matching points once you have a smaller parameter set?
Well, so you compute this sum well, you compute this. You compute the quality of match function. And those are two nested loops, one over the model points, one over the image points. And as you compute that, you just observe which of these have gone to 0. And when they've gone to 0, you just, well, when they're non-zero, you include them in a list of non-zero terms, and you use that list next time to eliminate, even computing values for the corresponding i's and j's. So you just keep track of which of these terms was non-zero while you compute the quality of match function.
Since that's done over intervals, you can prove that any further subdivision won't ever cause the thing to. Since you can bound it, it's like the minimum and the maximum is 0.
Right. So 0 means that this is actually interval 0, 0. I'm kind of being a little fuzzy here about you can actually do this either for pairs of i's and j's, or you can do it just for i's alone. So it turns out that probably doesn't make that much of a difference. Okay. So let me give you some idea of running times, and I actually don't know what. I don't actually remember what this. These are just ratios. So basically, the running times you get out of this are like alignment for kind of in the worst case, which is the case where there are no good matches, basically, where you just have uniformly random points. Well, I don't know whether that is the worst case. I mean, that's a bad case. Let's call it a bad case, because it's actually not clear what the worst case would be. But a commonly encountered bad case is basically where there's no good match. You're trying to find the best match among a lot of pretty poor matches, and in that case, it basically behaves like the alignment algorithm in terms of complexity. But if there's a good match present, it's much faster. Because it will do what you just saw in the slide where I showed you the exploration of parameter space. It will basically just zoom in on the correct solution very quickly. Okay, so that's the basic algorithm. Yeah.
Can you actually say running time, theoretical running time?
Well, that's actually a tricky question. I could, but it's not very meaningful. So in computational geometry, people usually use models of computation that are different from what you would need for analyzing this. This is for this kind of a traditional finite precision.
You can say have it in terms of your delta or your smallest subdivision.
Right. I mean, if you kind of in the limit, this is just going to refine the solution around the optimal match. So if you have one unique optimal match, then as you refine it more and more, you're just going to spend all your time refining the solution around that. Well, let's leave it at that. It's basically the question isn't really. It has a complicated answer. So I should say that I'm not really interested also in the computational geometry view of these problems. We'll see in a second some examples from layout analysis where you can actually, we'll get to that. So, yeah.
Maybe a practical question, but it is, if say the number of image points doubles, what's going to happen? And we're not changing anything. We're just doubling. Say, suppose you are trying to recognize your plane, and then just doubling the number of points in that day. So what's going to happen? Is the time is going to double?
Well, so do you want an asymptotic answer? So asymptotically, no. But asymptotically, in fact, that's not going to make any difference. But in practice, it's going to dominate. It's in fact going to dominate that's going to change the computation time quite a bit, and it's going to be like alignment. So if it's let's say if it's translation, rotation, and scale, then doubling the number of image points, I believe, would square the computation time. But that's not an asymptotic result, because that's basically all the computation that it performs initially to kind of zoom in on a good solution. Asymptotically, that time would still be dominant. If you actually let it run to to very high accuracy, that time would still be dominated by letting it run to very high accuracy. So
I guess the big O notation is pretty much worst case. So there's a branch and bound. So in theory, you could actually look at every possible interval until you reach a certain lower bound on some interval that will cut off or will go to 0. Right? You will enumerate all points in the search space of your intervals.
Well, actually, probably not. But that's actually separate. So that's actually an interesting question. Namely, for a given level of numerical accuracy that I desire, what's the number of boxes that will be expanded? And the worst case is not expanding everything. But that's a theoretically interesting question, but it's not actually one that matters much in practice. Also, I should say, so we'll get to that in a second. This is actually not the preferred way of implementing this now. So this is a simple way that I can explain to you quickly. An extension of this is to use interval Newton methods, which actually change the complexity picture slightly again. Yeah.
So how do you compare your method with Hausdorff matching in terms of accuracy and speed? And in terms of high-level intuition, there are all kinds of Hausdorff minimize the maximum duration, so cycle interval. How do you compare these two approaches?
So Hausdorff matching is just another metric that you can use it with this. So there's not. So that's what I was saying before about the use of Hausdorff matching. Hausdorff matching is this combination of picking a particular metric for which certain kinds of bounds computations are then easier. In this interval arithmetic framework, you can actually, Hausdorff matching is just one other possibility. There's nothing really complicated or special you need to do about it. There's a nice trick actually that you can use for basically taking one of these algorithms and doing Hausdorff matching with it, which is you do binary search kind of on the fraction that matches. So you can actually, you can set thresholds in this algorithm and say, try to find a solution that's better than this. And you can use that for actually just doing binary search for the error bound, for the epsilon that you need in order to match a given fraction. That was actually one of the original RAST algorithm in '92 already did that. And you can actually fold this into the search itself. So it turns out it's actually not much more expensive.
So that's another parameter of the transformation, T or something?
Well, usually you specify epsilon, and then you just match some number of features of the model. But you can also leave out the specification of epsilon and say, Hausdorff matching basically, Hausdorff matching in the way that, I don't know how Rutledge used the term, means that you specify the number of features you want to match or the fraction of features in the model you want to match, and then compute the error bound that makes that possible. And I'm saying you can either implement this directly in this framework and say our quality of match function is just, the epsilon, which we want to minimize, or you can implement it by using a bounded error matching algorithm, but doing a binary search until you've found exactly the epsilon for which you get the right number of matches. or the desired number of matches.
So the bound is used only to terminate it early? Like if I pick the bound of epsilon equals 0, then would it go on until the best solution will have an epsilon that is like 6.5 or 0.75, and then you know that that's the best solution in your search space, but it doesn't match your termination criteria of epsilon equals 0?
So there are two bounds here. So one is the error bound, which is fairly large and determined by the problem. So that's like 5 pixels or 10 pixels or whatever. The other bound is the accuracy bound. It's the numerical accuracy at which you terminate. And that's like, you can actually choose either an absolute or relative accuracy, and you can choose like 10 to the minus 4 or whatever. With interval Newton methods, it actually makes very little difference, because once you've zoomed in on a solution, then the interval Newton method will find the correct solution very quickly.
So this binary search on the would that be on the epsilon space, or would that be on the interval?
On the epsilon space. The accuracy, there are lots of different ways you can handle termination, and I just gave you a very simple one that works in practice. But you can actually say, I don't terminate before I prove that the best interval actually contains a solution that's guaranteed to be better than the one in the next interval. So then you're guaranteed that you really found the best solution. So let me tell you a bit more about a few computational tricks, just to give you some idea. So one question is that's very important in practical applications, and crucially important in applications to layout analysis, and that's to find n-best solutions. So we don't just want to find the best match, but we're going to find the 10 or 20 or 30 best matches. And we need to define what n-best means. A solution that, or definition that turns out to be fairly useful in practice is a greedy match, which you can think of as first finding the best solution. So we find the best instance of the model in the image, and then we remove all the image features that match that model, and we'll restart the search. Another way of defining n-best is to just require matches to parameter values that are different enough. So if we found something at translation 100, 100, we're not going to look at translations between 90 and 110. We're going to require all the solutions to have substantially different translations. This actually turns out to be computationally a little easier. It's a little harder to justify why you would want to do it, and it's hard to pick those parameters. So the greedy match actually turns out to be pretty good, and you can justify it in some simple probabilistic models of how images are generated. Anyway, there's actually a neat algorithmic trick, and let me just try and give you the flavor of it. And that's, instead of restarting this algorithm again and again on a new problem, we can actually fold this restart into the search itself. So inside the inner loop, we pop states of the priority queue. But if the state was generated before we actually found the last solution, then the quality of match may not be accurate anymore, because points that contributed to that quality of match may just not be available anymore for future matches. So we take that state, we reevaluate its quality of match, and we put it back on the priority queue without further consideration, and it will go in the right place in the priority queue and come up again when we need it. And that turns out to be computationally quite nice. So there are a bunch of improvements you can do to this that don't really work. There are kind of two improvements that people think of pretty quickly. One is to add point location data structures to try and speed up the computation of this. And it turns out that makes things worse compared to the matchlist approach, because it turns out you're better off basically splitting, going through another branch and bound step than actually using the point location data structure. And likewise, trying to there's a long paper that talks about benchmarks and comparisons and so on that actually where I try to justify these claims. But another thing one often says is, well, maybe we can identify promising regions in which to carry out the search, so that instead of doing branch and bound search on the entire range of parameters, we just pick a bunch of instead of performing branch and bound on the entire range of parameters, we just try to pre-identify a bunch of regions that are promising, and then start the search there. But that also tends to make things worse, because identifying these regions is actually pretty hard. And again, we can talk about it afterwards if you're interested. But this also comes back to the question of what's the computational complexity of this. There are also a bunch of improvements that do work, and they're kind of lots of little computational tricks, but they add up. So one thing is you can garbage collect the search queue based on lower bounds. If there is something that's below a lower bound of solution you've found, and you're kind of done, you can throw away all the stuff that's whose upper bounds are worse than that. It's important to pick splits carefully. So just subdividing the transformation space blindly gives you a much worse constant. I mean, it's just a constant factor, but it's a significant constant factor. It also helps to pick thresholds carefully. So there's an initial lower bound you can set on any match you're interested in, and if you pick that carefully, you save a lot of work. Also, you can conserve memory by, instead of using a priority queue, you can actually use a depth-first search, and that reduces the memory usage of this considerably, because you just need to keep one branch of the search tree in memory rather than a whole priority queue. But it means that the n-best solution string doesn't work anymore, so then you have to restart for finding multiple solutions. And then a lot of the techniques people have used in computer vision and with Huff transforms apply here. So you can use gradient information, for example. You can use connectedness information, etc. Okay, so let's look at any more questions about quick questions, or? Okay, so let's look at some other applications of this. So one is globally optimal robust least square line finding, which is roughly like what you would like to do with the Huff transform, but which is kind of hard to do with it. So this is kind of the abstract picture. This is an instance of that. And this is really nice, if you've ever tried to implement the Huff transform and get good solutions with it, that tends to be a certain amount of work. Here you basically just pick the error bound and go. And it's actually fairly robust to the kind of error bound you pick. Here's an extension to text line finding, which has turned out to be quite useful in practice. So instead of two line parameters, namely rho and theta for just a simple line match, we use 3 line parameters. Two line parameters for describing the baseline, and then 1 parameter for describing how far the line of descenders is from the baseline. And that gives rise to a quality of match function like this. And when we apply that, one advantage this approach has over other text line finding methods is that it doesn't assume that the text lines are parallel on the page. So we can take a prospectively distorted picture of a page like this. Well, here, just clean it up, and perform line finding on it. So these are all the green ones are all the horizontal text lines, and the vertical lines are actually column boundaries. And we can actually use it for dewarping. It turns out that for document analysis, this isn't quite sufficient, because if you try to apply a text line finder like that to a document, you get problems like these, namely that it will find text lines that cross column boundaries, and there's no guarantee that text lines in different columns are aligned with one another. So one way of formulating this problem abstractly is to say, let's try to find maximum constrained text line segments. So we're trying to find line segments or text line segments in the case of text that are a robust least square match to points, but that don't cross any of the number of given obstacles. So if you try to solve something like this in a traditional computational geometry framework, that may be fairly tricky, but it turns out formulated as an interval arithmetic optimization problem, it's quite simple. And in fact, so this is actually a 5-parameter problem, the start and end of each line segment, plus the descenders for constrained text line finding. But there's actually a neat little computational trick that still lets us solve this as a 3-parameter problem. Because basically the endpoints are kind of implicitly given by where the obstacles are. So these are examples of, this is obviously a constructed example, but this is an application of this method to text, and there's just one obstacle here, this column separator. And the text line, the matched text lines just stop there.
How's the obstacle generated?
Well, that's going to come in a few slides. Here is so you can also do this with nonlinear functions. This is a polynomial baseline model, and this is an example application to that. So this is basically globally optimal, robust least square polynomial fitting, and the input is you actually see the text back here, but the input to the algorithm is actually just the green points. So there's.
How are they found? How are they found? The green points.
Oh, they're the bottom centers of the bounding boxes of connected components. Here's another application, which is globally optimal robust least square fitting of circles and ellipses, which is another topic that has generated probably hundreds of papers in the computer vision literature. Again, this is a fairly straightforward application of these interval arithmetic optimization approaches, and actually it works even nicer with the interval Newton methods, because this involves a lot of parametric optimization kind of down the search tree, and for that the interval Newton methods actually help quite a bit. We can also play other tricks. For example, we can find line segments with constraints like they shouldn't have any gaps larger than a certain amount, and we can incorporate such things into the cost function. So there are a lot of things that, on the face may seem pretty complicated in kind of traditional computer vision or image processing things that are fairly easy modifications to cost functions here. Now, I won't have time to go through it, but I should just mention that there's actually a special branch and bound version, or a special branch and bound algorithm for finding maximum empty rectangles that are axis aligned. And that's just, it's actually a neat little algorithm, but we won't have time to go through it. But let me just show you some results. This is actually the whole, this is actually the whole algorithm in Python. The traditional computational geometry way of doing this is with sweeps, and it's pretty tricky also because you get degeneracies and so on. For actual applications, so maximum empty rectangles have been used by Baird and Fortune and others for document layout analysis, and that's a nice. So if you apply it in the way they did, you get you get a fairly nice separation of text from background, and you kind of find major divisions. But it's hard to actually identify all the white space that's meaningful for layout analysis, or rather you often identify too much white space, so you'll find separators that aren't actually useful. It turns out there's a simple modification you can do to the objective function for maximum white space rectangles, and that's to incorporate a halo where you require the perimeter of the empty rectangle to contain a certain number of connected components. So more concretely, when you apply this to real documents, the halo is text, is characters. And if you use this objective function where you look for, so there are a few ingredients that go into this objective function. You want long, you want tall and narrow things, and you want a halo that's full. So you want many adjacent connected components that correspond to characters. And if you write down such an objective function, it's actually fairly robust to the details of the parameters and the detailed form. But you get results like these. So the green stuff is white space that was found by these algorithms that corresponds basically to column separators. Oops. So we can also do this for non-axis aligned rectangles, for which the special trick, the special axis aligned algorithm doesn't work. We're back to normal optimization. And we could, so one simple way of doing this is to optimize the indicator function for the predicate that the overlap of the rectangle we have with the obstacles is 0. So this is a step function. It's but it turns out that's fairly slow. It's actually easier, it's actually faster to maximize the height of this rectangle given its center, its angle, and its width. And if we maximize this over the entire space, we get the maximum unaligned empty rectangle. So there's an example of that, again, for a document. And you can do this with halos as well. To do column boundary finding basically at arbitrary orientations. Two other applications I should mention is one is you can apply this to globally optimal mixture estimation. So we have a mixture of two Gaussians, for example, and a bunch of samples, and you try and fit kind of the optimal mixture parameters. Obviously, you can't do this for Gaussians with lots of parameters. We're always talking for these kinds of algorithms, R4, R5, or something. But people still use EM for these kinds of things. Robust linear regression is another example where this works nicely. So this is the I think the solid line is the original line, and the dashed line is the globally optimal robust linear regression, and this is just a simple least square regression.
What do you mean by the original?
So that's what the data was generated from. So the data was generated by taking two lines, sampling from them, adding Gaussian noise, and then for fitting, performing robust linear regression. Okay, so what I've shown you is a quick overview of interval arithmetic. I've shown you branch and bound optimization using interval arithmetic for the bounds computation. And we've seen applications to a number of geometric problems, like geometric matching, finding geometric primitives, geometric layout analysis, and a few non-geometric statistical problems. What I didn't really discuss was detailed performance analysis, profiling, and search strategies. So there's a CZIU paper that talks about that in great detail. And then using interval Newton methods, which turn out to not help much with the initial parts of the branch and bound algorithm, because they basically have to go through the same kind of splitting, but they speed up the final stages of the optimization. And there are lots of other applications and algorithms that I didn't talk about. So there are some applications to 3D data sets we're working on now, incorporation of grouping and segmentation, interpretation of line drawings, so maps and that sort of thing. So you can use this for finding lines, dashed lines, boxes, arrows, etc. in document images or in drawings. There's actually applications to ray tracing and applications to pattern recognition. So I think I should stop here. There's a bit more detail on the layout analysis. Let's just see whether I can, since people asked about running times, let me just see whether I can find those plots. So this is the, this is running times, oh, this is actually in Java, including all I/O. So running times are, 0. This is connected components on the UW3 database. These are running times in seconds. So for images from the UW3 database. And for the constrained text line finding, these are the running times on the UW3 database. Again, this is in Java on a 1 gigahertz PC. So it's pretty fast. And of course, Intel and AMD are helping. So these are going down. Okay, well, thank you very much.
Let me say that Tom, during his month visit here, is putting together some C# code that actually implements many of these things. So that should be available to people if they would like to take a look at working implementations.